To the 2008 Summer Lecture Series. The Communications Department has been sponsoring this for almost 20 years now. And we have a tradition of trying to get the representatives of the most cutting-edge science that's happening at the lab to describe it to you in terms that all of us can understand, even if you're not in their department. We're going to continue that today with Wes Bethel, who's the leader of the visualization group and the Computational Research Division. Before I introduce Wes, there's a couple of little things I got to get out of the way. One of them is we don't have a problem yet because nobody is sitting in the aisles, but lots of times people who come in later will sit down in the aisle instead of trying to make their way into the seats. So if one of them sits down by you, please ask that person to take a real seat. There are enough to accommodate people. And I wanted to tell you about next week's summer lecture, which is going to be by Sarabi Menon, who's going to talk about regional and global climate change and the role that particles and gases play in that. And that's a topic that's becoming I would say an urgent one, so I hope that all of you will come and hear that. So let me introduce Wes. Sorry, Wes. Oops. I'm going to have to straighten my tongue out here. Wes, as I mentioned earlier, is going to tell us about scientific visualization, which he describes as a modern oscilloscope for seeing the unseeable. And if there's anybody in the audience who doesn't remember what an oscilloscope is, I think Wes will probably tell us what that is before he begins. Bethel has been a staff scientist at Berkeley Lab since 1990 and the leader of the Computational Research Division Scientific Visualization Group. Those activities of that group include both visualization research and the production and analytics of visualizations from databases that are often immense. Both these areas focus on increasing scientific productivity through better technologies for understanding data visually. Bethel's interests include computer graphics and visualization software architecture, remote and distributed visualization algorithms, and latency-tolerant and parallel graphics techniques, which I hope he will also define for us. He received his master's degree in computer science from the University of Tulsa in 1986, and he's a member of the Association for Computing Machinery, ACM, which is the world's largest educational and scientific computing society, plus SIGGRAPH, which is the ACM's special interest group on graphics and interactive techniques, and he's a member of the Institute of Electrical and Electronics Engineers. So let's welcome Wes Bethel.
Thank you, Paul. So Paul asked me for a bio that was a little more spicy than the one that he just gave you. And I said, I really prefer to keep a low profile. But one other bit of bio that Paul didn't get out is that I also have a pilot's license. And one of the things that pilots do before they take off is they do a safety briefing. And as I was standing up here putting the laptop together, I see this the safety briefing card here on the podium. And oddly enough, nobody's ever read it to me before, so I'm going to read it to you. It says, please observe these instructions in the event of an earthquake or fire alarm. In the event of an earthquake, duck, cover, and hold. Immediately duck as low as possible between the auditorium seat rows or in a nearby doorway, threshold, or corner of the room. Hold on to the protection. When the shaking stops or if the fire alarm is heard, proceed to the nearest fire exit. There's one right there, there's one back there, there's one back there. Okay, so with our safety briefing out of the way, buckle your seatbelts and let's go. Can you imagine going to the doctor for surgery and the first time he sees what's inside of you is when he whips out his scalpel and carves you open? Wouldn't that be alarming? Well, that's how it used to be. So this project is kind of interesting. I have several examples here where I'm just going to try and convince you that Viz is, in fact, a way to see the unseeable. There was a project called The Visible Human. They took a cadaver, they digitized him, and they did a lot of interesting stuff with the data that they collected. And so this example is a multi-resolution representation of a part of the hand. And so you get a coarse view when you're far away, and then when you zoom in, you get more details. And I understand that there's also circulatory models that have been developed based on this data. So there's more interactive stuff. And this is used for microsurgery training for doctors. So this would be a great thing to have, and I bet the doctors a few hundred years ago would have loved to have had this kind of thing. So here's another interesting example. It shows the path taken by a humpback whale. So this is sort of a combination of real data that was collected by a sensor, and here's some artwork that shows the hump, and I guess that's a sensor that they duct tape or stapled onto the whale while he's swimming around. Yes?
Can somebody dim the house lights so we can see?
Oh, that's a splendid idea. Well, while they're working on that, I'll continue. So what this data shows is the path taken by the whale, and these little sawtooth things show the whale propelling himself with tail motion. And so a couple of interesting things that had never been seen before came about when viewing this data. One was that this particular whale glided down and swam up. Right? So unless you're down there with the whale, you're never going to see that. Another is some interesting sort of rolling behavior. This particular species of whale likes to do a sort of a barrel roll kind of thing when he's grabbing fish underwater. Well, how would you have ever seen that before unless you had some way to collect and look at some interesting data?
Was there velocity information?
There probably is.
Was that a plan view?
Was that a plan view? No, that was a 3D view. So I guess this would be like the top of the water, and so you're sort of underwater looking down in a little bit. Yeah. Okay, so here's another example. This is a picture of trouble, big trouble in a network. Here's actually a view of a year's worth of network connection data. It's about a quarter of terabyte in size. This is a drilled-in view. It shows regular malicious activity occurring at 9:15 local time every day. Doing a bit more visual analysis on that data, what we see is one of these events is a distributed scan of one of the networks here at Berkeley Lab, and then by doing some reverse mapping, we can trace that back to a set of identified hosts who are participating in this attack. In this particular example, each of the individual hosts is assigned a different destination block of address space. So it was like a gang of bullies all picking on a different part of the network space. So this example, this is supposed to be a movie. It's not playing. So I have some more examples about this one later on. So anyway, there's 4 quick examples. What I hope that you leave here with today is the impression that graphics and visualization is really an interesting problem-rich environment. In order to lead you to that conclusion, I have to have you go down a couple of paths. One's computer graphics. I'm really going to drill into computer graphics because it is the basis for visualization. And if you understand the graphics pipeline, you will probably understand the visualization pipeline, and it gives me the lattice work upon which I can talk about some of the challenges in visualization and graphics. Okay, so let's get started. What's computer graphics and what's visualization? So graphics is the transformation of data into images. There's been a long history of devices for producing images, pen plotters. I actually programmed those things way back when. Storage tubes, and it wasn't until the first raster display, with pixels on the screen, that technology was invented actually just about the time I was getting out of graduate school. That was pretty scary. So there's been a lot of interesting devices over the years. Okay, so graphics is transformation of data into images. Visualization is also the transformation of data into images. How about that? Well, so what's the difference? Well, we'll talk about that. You'll understand better as we go through it. A high-level point here: graphics and visualization. It's this interesting mix of computer science, cognitive science. So how do you effectively present information? Math, industrial engineering, and a whole bunch of other things. So if you talk to one graphics guy or one viz person, that person is going to be a lot different from the next one that you talk to. They're going to have different emphasis areas. Okay, graphics tends to focus on the process of rendering. So how do you best turn triangles into pixels or strokes of the pen, right? Visualization tends to focus more on the mapping of abstract data, so temperature, density, whale tail movement, into things that you can actually render. And the distinction between the two often becomes blurry. So why computer graphics and visualization? The short answer is that we have this great high bandwidth system right into our head. Right? It's our eyes. We're innately visual creatures. We grow up learning at an early age how to interact and understand and gain knowledge from the world around us. And so it makes perfect sense that we can leverage this machinery that nature has given us to accelerate scientific knowledge discovery. Okay, so some history. If we start in the present and work our way backwards, so we're all pretty familiar with the idea of making pictures with computers. Well, before computers, people made pictures of ideas that they wanted to convey to others with cameras, right? Well, going back in time even more, the Renaissance masters were the first ones to generate, accurate images of buildings and other people. People, that would be kind of interesting. And so there's some mathematics of perspective geometry that I'm going to introduce you to in a couple of slides. Then there's also, a rich history of art and painting, effective use of color, and that sort of thing. All of these fields form the latticework, the basis for effective computer graphics. There's also this interesting device over here. It's called an orrery, O-R-R-E-R-Y, which is I think this one's a model of the solar system. So, the sun's in the middle, and these guys rotate around, and the little moons rotate around the planets. And so, that's an effective visualization tool as well, right? So somebody had to come up with the model, the idea for the model of that thing, right? You got planets, and you got moons going around the planets. And then you have somebody that built the model. The building of the model is the computer graphics equivalent of graphics and viz. It's the expression of the idea into something that you can actually see. So if you dig around in art history, you'll learn that some of the first early attempts at creating images of reality were people drawing outlines of things, drawing outlines around the shadows cast by objects. Before that, paintings consisted of cartoon-like antelopes on cave walls and that sort of thing. So the point here is that during the dawn of civilization, man became more adept at accurate depiction of shapes through artwork. This idea was refined in the early Renaissance with the use of perspective. So a pre-Renaissance painting shows a scene with a bunch of people in it, and the perspective is wrong. And it wasn't until the early Renaissance with Leonardo da Vinci where you begin to see correct perspective. So here you see parallel lines converging to a point as off in the distance. So this is called perspective projection. Now, there's actually a whole family of different types of projections. The CAD community is very fond of what are called parallel projections, and the idea is that parallel lines, in fact, do not converge at infinity, and that's so that you can take measurements of different things in the scene and see how long pieces and parts actually are. Okay, so there's perspective geometry, then there's also the effective use of color. Quick introduction to color theory. There's additive color, which is light. So white light is composed of light of all frequencies, and if you run a white light through a prism, you can see that. Subtractive colors are those where if you add more and more stuff, you get black, right? Computer screens and most of what we deal with in graphics is the additive ones. The subtractive ones are the domain of printers. Okay, so here's a couple of slides on how you use color. One is to indicate set membership, and so up here we see the different colors mapping to political boundaries. You can see at a glance that one country's colored, one colored, and so on and so forth. Another use of color is to indicate measurement. So in this case, we're looking at the altitude of the topography in the state of California. Okay. Another use of color is decoration, like this yahoo who's swinging a golf club wearing these obnoxious pants. And then finally, we have color as a representation of reality, to help represent reality. And so this is what the Renaissance art masters excelled in, was effective use of color to represent reality. To point out what I mean by representing reality, if you look at this guy here, this picture of this cube, at a glance you can guesstimate that maybe the light's coming from up here on the upper right because there's a shadow and because this side is brighter than the side that is not directly illuminated by the shadow. Okay, so representing reality. Now, if we look at the difference between graphics and visualization, in the top row, we're actually using color to encode information. And so at a glance, you can derive understanding based on color. You can say, well, here's a bunch of countries in Africa, and if you know what the color scale is, you can go, wow, that looks really high, and this looks pretty low, right? So that's pretty useful. Whereas on the bottom row, color represents something else. It's used to represent reality or to be decoration. For the past 3 decades in computer graphics research, they have been on a quest for photorealism. So make a picture using software that's completely indistinguishable from a photograph. And color plays into this quite prominently. This picture doesn't show up so well here with this projector, but on a high-resolution monitor, there's a rich set of textures that are visible in this image. There's nice, the tiles look flat. They look very terracotta-like. The tile work around the fountain here is glossy. It's shiny. You see nice reflections in the water. You see refractions in the water. So there's a lot of stuff going on in this picture. Whereas in visualization, the use of color is to help enable insight. And so here's some examples that show that happening. So in visualization, here's an example of a good use of color. We're using background colors from nature to indicate sort of background parts of the scene. So greens are a good background color. And we're using reds and yellows to indicate regions that we want to draw your eye to. So I was having a discussion a couple of weeks ago with a colleague, and he pointed out that humans' attraction to reds and yellows stems from our simian ancestry, where the ripe fruits hanging in the trees are yellow and red, right? So that's kind of interesting. Our stomachs drive our understanding. So that's pretty neat. Here's a bad use of color. This hue ramp is the default in many visualization packages, and it's just the absolute worst thing that you can use because it introduces optical illusions. It creates contours in the data that your eyes are drawn to, that those contours don't actually exist. So as you go forward in your scientific career, begin to put together visualizations, you have to think about what problem am I trying to solve? What idea am I trying to convey? What's the best way that I can do that? So here's an example of a couple of different color maps applied to a given data set. So the authors of this particular paper began with the standard hue ramp and applied it this is actually a simulation of a thunderstorm, and they took a slice out of it. And so we're looking at a slice of a thunderstorm model. Default color map. Over here, what they did was they made the low values white, and so when they did that, all of a sudden you begin to see some structure in the data that you couldn't see before, right? Just with a little bit of color table modification. Now, if we proceed over here, what we've done is just used a gray map, and so what we've done is removed the 1 + 1 = 3 optical illusion effect that occurs when you use hue maps. But then the bad thing is that we've lost visibly a lot of the structure and information that was in the data. If we have a constant hue here and increased saturation and brightness, then we get a different effect. The best visualization color maps tend to be those that use not just a single hue, but maybe a couple of close ones, a couple of nearby close ones, combined with changes in saturation and value. These help your eye better understand the structure of data. Now, there's other examples where you may actually want to use like a color table with 7 colors in it. so that at a glance you can say, at this region of the data, the underlying data is within a certain numerical range, and there's use cases when that's appropriate. Let's see here. Okay, so hope your seatbelts are still fastened. We're about to jump deeper into the computer graphics world. The central problem in computer graphics is this shading equation, and the basic idea is that given a collection of objects and scene parameters, compute the color visible at each pixel on the screen. And there's two broad approaches for doing this. One is where you take your pile of objects and you look at each one and you figure out which screen pixels this object covers, and you paint them. And you grab the next object and you paint all the screen pixels, and so on and so forth. The other approach is called image order, where you march through the pixels and you figure out which objects in your object database intersect that pixel, and you compute the color that way. Okay, so image order and object order. So I'm going to drag you through an introduction to ray tracing, which is the keystone image order algorithm in computer graphics. Interestingly, ray tracing didn't really make an appearance in our field until about 1980. And the basic idea is that you want to compute how much light is reflected back to the viewer, you, through each pixel, through a combination of light and material properties of objects in the scene. So it sounds pretty simple. And in fact, this is just sort of the first half of the rendering equation. So don't be intimidated by all of this stuff. I'll tell you what it means. Remember what I said previously. We're computing the amount of light that's reflected back to you as a combination of a bunch of stuff. And so here's the light that's reflected back to you, and here's a combination of a bunch of stuff, right? It's pretty easy. So what is that bunch of stuff? There's a bunch of ambient light that's bouncing around in the scene. There's diffuse reflections, and then there's specular reflections. So specular reflections are those that depend upon the relationship between the light source, the object, and you. So, guys over here are probably blinded by the specular reflection of the light off my bald head. Whereas if I turn around this way, except for that spot right there, this side of my head's going to be brighter than this side, but without the specular highlight, right? So diffuse and specular reflection. So this is where being bald actually comes in handy. Yeah.
What's the unit for this? Units?
What's the unit for what?
Reflective intensity is measured in.
I'm sorry?
What's reflective intensity is?
Oh, well, so pixel, it doesn't matter, right? So it could be 0 to 255, it could be 0 to 1, so on and so forth. So if you go backwards into the scene, you have to assign luminance values to each of the light sources, and those are typically values in the range 0 to 1. And all of this stuff sums up to a value that's between 0 and 1. Does that make sense? Okay. All right, so what Turner-Whitted did to prove upon the rendering equation to make it ray tracing was he said, so at each intersection point between my eye and each object in the scene, previously the idea was the color of the object in the scene was the sum of all the light sources shining off of that object in the scene. What Turner did was he added some more stuff to it that says, well, it's all, the light source contributions are not just light sources, but also light bouncing off of other objects in the scene. All right, so if you imagine a mirrored ball, right, you can see a lot of stuff elsewhere in the scene, and that's what this stuff says. So there's stuff that's reflected, and then there's stuff that's refracted. So reflection and refraction. And here's a picture of what that looks like. Here you are, you're looking through the scene. Here's a ray that intersects the object. There's a ray that goes off to the light source. There's a reflected ray. And I have some other examples coming up here where we'll look at this more closely, as well as refracted rays. Okay, so here we are, virtual viewpoint. We shoot a ray through the scene. We don't hit anything, and so we'll paint that pixel black. Over here, we'll shoot a ray through the scene, and we hit something, and so we'll paint the picture, whatever that color is. Okay, so shadow rays, just by example, we shoot a ray into the scene, we intersect an object, we shoot a ray off to the light source, and because we don't hit anything on the way to the light source, we know that we're not in a shadow. Whereas over here, we shoot a ray into the scene, shoot a ray off to the light source, and we run into something, so we're in a shadow. And so here, this image shows a shadow cast by the ball. Here's the use of color. Here's our light source up here, shining down like that. Okay, reflected rays, pretty obvious. You shoot a ray into the scene, and you then, it reflects. Shoot the ray off and see what it hits. And here's a nice image showing the reflection of the checkerboard in this mirrored ball. Now, one of the attributes that you can tune in ray tracing code is the number of reflection and refraction bounces in the rays. And so this example shows, no bounces, 1 bounce, and 2 bounce. So in this example, you see the backside of this collection of balls, and over here you begin to see, multiple reflections in the mirrored surface. Okay, and refracted rays, same deal. Shoot a ray, it hits something. If the surface has a surface property that supports refraction, then you would shoot a refraction ray. And here's an example of the mandrel image being seen via refraction on the top of the sphere over here. Okay, so you would think that since ray tracing is performed such that at each pixel we compute some stuff, that it would be trivially parallelizable, and in fact it is. But there's some problems. One is that you have to replicate the scene at each processing element that's carrying out this calculation, and so if you have a large and complex scene, it's not going to work. Another challenge is load balancing and effective data distribution as you go through this process. And that's about the extent that I'm going to talk about parallelizing ray tracing. Okay, so to help introduce you to a different view of the graphics pipeline and the visualization pipeline, I'm going to show you an object order view of computer graphics vis-a-vis graphics APIs. And we're going to be dragged down the graphics pipeline. Okay, so there's 2 broad families of graphics APIs. One's declarative, the other's imperative. And so in declarative, you say, I want a tree, and I want a sphere, and I want a cone, and I want a chair, and put my camera here and a light source there and draw it. With imperative, so declarative is a very high-level thing. There's commercial products, well, actually Performer's sort of out of business now, but they were the gold standard in our industry for a long time, used for flight simulators and visual simulation. Imperative, on the other hand, is a very verbose API. It's a very verbose way of specifying graphics calls. So you're not saying, give me a sphere or a triangle or a tree. You're saying, draw a line here, draw a triangle there, which is much different. OpenGL is a declarative API. It's the industry standard. It's supported on all modern graphics hardwares. It does have higher level, it has basic primitives, lines, triangles, and points, and then there are auxiliary libraries that support non-uniform rational B-splines, quadrics, and that sort of thing. But those are built using the underlying primitives. It supports a Phong lighting model, but not Gros shading. So it was that first version of the shading equation that I showed you. So none of this reflection, refraction stuff. And don't worry about the difference between Phong and Gros shading. So here's some example code for this, for OpenGL. So over here, we're going to draw a red triangle. We say, hey, I'm drawing a triangle. Hey, the color's red. Here's a vertex, here's a vertex, here's a vertex, and then draw it. And that's what you got. We're going to draw another triangle over here, but this time, instead of using the same color for the entire triangle, we're going to say this vertex is red, the next one's blue, the next one's blue, and then draw it, and this is what you get. So in Gros shading, what you get is interpolation of color, so between blue and red along each of these edges. Okay, so when the application issues those draw commands that I just showed you, what happens next? Okay, well, I'm going to show you. I have several slides on what happens next. So each command dispatches objects. Those are buffered up. They're scan converted into pixel fragments. If you don't know what that means, don't worry, I'll explain. They're textured, they're shaded, they're fogged, they're stenciled, they're clipped, they're alpha blended, and finally they pop up on the screen as pixels. And if you don't understand any of that stuff, don't worry about it. I'll give you a hint here in a second. Okay, so what kind of applications are we talking about? Well, there could be visual simulation applications, flight simulators, visualizations, graphics, Doom 3. It doesn't matter. Okay, there's most graphics applications these days are written using a declarative API, either OpenGL or Direct3D. So after the application issues its commands, they're buffered up by the OpenGL implementation. I'm talking about OpenGL here. In the geometry engine, the vertices are transformed. So there's the perspective transformation stuff I was talking about earlier. You can move the vertices around. They are lit. They're shaded. So at this stage, the graphics card computes the shade of each of the triangles based upon where you've put the lights in the scene. And then the results are passed on downstream, where you have a lit shaded triangle, and next you have to figure out what pixels on the screen are actually covered by that triangle. That's what rasterization is. You may want to texture it so that you can have the appearance of finer surface detail. Imagine, look at this carpet here, right? If you imagine the complexity of the model, if you wanted to have a triangle for each little fiber of carpet, that would be just crazy, right? It would be such a huge model that it would be impractical to draw. But what you can do is you can cheat. You can take a camera and take a picture of the carpet and then paste that picture onto one triangle, right? So you have this really cheap model, one triangle, but it has huge amount of visual fidelity. It looks like the carpet. And that effect is used in computer games a lot. Fragment operations include things like stenciling if you want to create little cutouts, alpha blending, you want to blend pixels on top of pixels, that sort of thing. And then finally, they're popped up on the screen. So a couple of quick slides about parallelism and graphics. Okay, again, think from a high level, we have this pipeline of stuff going from application all the way down to pixels showing up on the screen. How can we parallelize that? How can we make it go faster? Well, there's a couple of different ways that you can do it. One is that you can have task parallelism, where you have parts of this pipeline operating concurrently with other parts of the pipeline. So you have earlier data at later stages in the pipeline and later data at earlier stages in the pipeline. It's like an assembly line where they build cars, right? The other way to do it is that you might have a bunch of these operating in parallel. So one pipeline's computing image at time 0, another one computing at time 1, and so on and so forth. Okay, so fast forwarding to today, the NVIDIA 8800 GTX Ultra, that's a graphics processor that you can buy for $300, has 16 onboard processors, each of which can support 768 threads each, which means that you can have at once over 12,000 simultaneous execution threads in flight at once. Wow, that's really amazing. Who would have thunk it? This is really amazing to those of us who wrote code that actually pushed pens around on pen pliers. What are all those guys working on? Well, remember our graphics pipeline, transform and light, rasterization, fragment operations. All those 12,000 threads are working on all that stuff at once. And so that's how this guy is able to draw 200 million triangles a second for $300. It's just amazing. All right, so what about programming the GPUs? There's the old way, and by old I mean like last year, right? And what you had were things called vertex and fragment programs. Okay, if I back up here, remember we have, okay, so at this stage during transformation and lighting, that's called a vertex operation. And then down here when we get to fragment operations, that's a fragment operation. Okay, so coding consisted of writing stuff that looked like assembler language. If you don't know what assembler language is, don't worry. If you know what it is, you know what I'm talking about. Trust me, this is painful. It's error prone, it's non-portable because the vendors couldn't agree on a standard, so on and so forth. More recently, there's a new way to do it called the Compute Unified Device Architecture, aka CUDA, from NVIDIA, which is basically C language with extensions for multi-threading. So before, right, it would be really hard, if you wanted to write like scientific computing code, like solve the heat equation, it'd be really hard because you'd have to cast it as a vertex or fragment program operation. It's like reaching through your leg to scratch your back. Here, you can actually just write the code and have a couple of places where you worry about parallelism. This is great. Why bother with this? Well, there was an article that came out the other day that talked about NVIDIA's new Tesla-based system based on their R10K chips. They get a teraflop off a GPU. Teraflop, one GPU. Whereas, with our best CPUs, we're sort of in the gigaflop range. Amazing. All right, so on to visualization, which is what you paid to come see. Visualization is the transformation of abstract data into images. Remember this graphics pipeline. Wow, we've been talking about that for the past 10 minutes or so. Well, so visualization is dumping data into this process. Let's see. So viz algorithms are those that turn data into things that you can draw. Hence the close relationship between visualization and graphics. I'm going to hit you with 3 quick examples of visualization research. So circa 1993, give or take, there were some earth scientists here at LBL who had this finite difference simulation that modeled fluid flow. It was a two-phase or three-phase fluid flow code that modeled movement of water, gas, and oil through porous media, rock. And it was in use by the oil companies, among others, to model their petroleum reservoirs. So I had an uncle who was a geologist for Sun Oil Company in West Texas back in the Wildcat days. And what they would do is they would walk out, and he'd scratch his head, and he'd point at the ground, and they'd drill a hole in the ground, and oil would squirt out. And then after a few years, the oil would stop squirting out, but still 95% of the oil was underground. It was just the pressure of the rocks that pushed the oil out. So there was a big push by the oil companies to figure out how to get the rest of that oil out of the ground, hence these reservoir models. So the basic idea here is that we have an injection well where we pump stuff in, and then we have production wells that surround it where we pump stuff out. And the problem that they were trying to optimize is to where do you put the wells, right? Because it costs a lot of money to drill the wells. So the visualization project in this case aimed to allow a person who knew something about rocks and wells and oil to go in and quickly place the wells and run the simulation and get some answers back and that sort of thing. I actually took a machine down to New Orleans and Houston for a couple of conferences, and the proof in the pudding for me was when a guy with a big old cowboy hat and a cigar came up. Hey, boy, how are you doing? And I'm like, explain the problem. It's like, where do you put the well? He's like, put it right over there. And I said, no, you do it. And I had a little VR device, and he walked up and grabbed the thing and pushed the well over and pushed a button, and the simulation restarted. A guy who'd never seen a computer before, basically, was doing petroleum reservoir modeling, exploring a highly dimensional parameter space for which there was no solution. This was an effective use of visualization because it presented a very simple interface that my uncle could understand to solve a very complex problem. Another example, I see Sylvia's here, so hopefully I won't butcher this one too bad. This one was circa about year 2000. The problem that Dr. Crivelli was trying to solve is to find the optimal structure of a protein. So given a sequence of amino acids, these fold up into this nice three-dimensional shape that has minimum energy. Right? If you arrange them the wrong way, then the molecule has high energy, and it's it's just not feasible in nature. Interestingly, nature knows the answer to this problem, but solving it computationally is MP hard. So what does that mean? Well, if you're not a computer scientist, what that means is that you have to try all possible combinations of configurations. That's MP complete. MP hard is when those combinations involve a continuous parameter space. So it's not just combinatorial, it's also continuous. Okay, so it's basically not solvable. So the idea that Dr. Crivelli had was, well, can we set up the problem to begin with in a way that will help accelerate its time to solution? And that was the idea. And so the idea was to put together a visualization application that would take this string of amino acids, allow her, the expert user, to manipulate the protein molecule into a shape that she thought was a good one that wasn't going to get stuck at a local minimum during optimization and dispatch it off. And so this example shows interrupting the simulation which was running on a large parallel machine and looking at all the different combinations that this thing was running on and pruning entire branches from this exploration tree to converge towards solution more quickly. And so this image shows the shape of the protein plus some energy visualization. And so Dr. Crivelli has used this methodology quite successfully for the past 2 or 3 biennial CASP competitions where teams from around the world work to predict protein structure for unknown molecules. Did I get that right? Okay, good. Okay, another example is to how do you go about understanding the impact of various parameters on Rayleigh-Taylor instability? Rayleigh-Taylor instability is when you have a heavy fluid on top and light fluid on the bottom, and as you evolve the simulation, or if there's a physical process, these two things mix and governed by these equations. So some colleagues at Lawrence Livermore Lab worked on a methodology for doing topological analysis to identify, count, and track mixing regions. And they were interested in comparing results of simulations that were run on different machines at different resolutions, at different time steps, and so on and so forth. And so it turned out, the punchline here is that topological analysis was the correct basis for doing the analysis and the comparison. So by bubble regions, I don't know how well you guys can see this in the back. In early stages of the simulation, you have, if you color all the bubbles, that sort of looks like carpet. And over time, the bubbles get larger and larger and larger until they, appear sort of more like cauliflower or something. The turbulence scientists had to work closely with my colleagues at Lawrence Livermore to come up with a good definition of what's a bubble so that they could compute it and track it and count it. So this was a huge amount of work. This was a couple of years worth of visualization research that allowed them to come up with a way of comparing one Rayleigh-Taylor simulation with another. And what they find is that they're actually in pretty good agreement. So this was useful information for this particular program. Okay, so back to the high-level view about visualization. Here's the map of the problem space that we Viz people have to deal with. Okay, I've showed you a graphics pipeline. I've showed you pipeline after pipeline after pipeline, and hopefully your mind is going, oh yeah, boy, here's another one. Well, it's really the same one, but it's kind of rearranged differently. We have to deal with data coming from simulation and experiment. We do analysis on it, which includes visualization and traditional data analysis, and we present results. Underpinning all of this stuff is a huge data management problem. I/O libraries, we're worried about high-performance I/O. Some folks are interested in automating all of this stuff, which is called workflow processing. This is just a huge problem area. And when we do this all interactively, that's referred to as analytics, so data mining and analytics. Okay, so the problems that we face are that the machines get bigger, there's increased parallelism, there's heterogeneous architectures. As a result, data becomes larger, we have increased spatial resolution, more variables, more time steps, and there's secondary problems that result because of this. Our scientific colleagues want to compare the results of one simulation versus another. They want to compare experiments and simulation. And the really big problem here is there's just too darn much information. It turns out that our ability to create and store information exceeds our capacity to understand it. As Herbert Simon said, information requires attention to process, and so the more of it you have, the less attention you have to give it, right? A wealth of information creates a poverty of attention. That's great. And the scientific data management community, in a series of workshops a couple of years ago, put out a report that said that one of the bottlenecks in modern science is managing and gaining insight from data. So let me give you a view of why this is the case. I have a couple of slides on Moore's law. Moore said that the transistor count on chips will double every 18 months or 3 years or something. And from 71 to 2004, yep, you see all of these processors, and the transistor density is this axis. And indeed, that claim, that prediction seems to be holding true. Well, not only are processors getting faster, but our ability to store data is growing at a commensurate rate. So here's PC hard drive capacity over time. Oh, and you think, well, so we can compute it, we can store it, but we can also collect it, right? Because cameras are becoming more dense at a higher resolution at a rate that follows Moore's law. So what's a poor guy to do? Oh, and so ESNet, a petabyte per month is history as of the middle of 2006. I bet those guys wish that they were back to sub-petabyte levels, which is now 18 months, 2 years ago. It's just amazing. All right, so with all of that data, what's a guy to do? All right, the problem here, thanks to Cecilia Aragon for this slide, who she obtained from Jeffrey here at Palo Alto Research Center. As all of this data in the world goes up and up and up, and this is a cartoon slide, the problem is that we have finite human cognitive capacity. So we have a poverty of attention. No big surprise there. All right, so how do we viz guys and how do the media abuse cognitive bandwidth? Well, I call it the meat grinder syndrome, right? If you got more data, right, make a bigger meat grinder and you put out, increased amount of pixels. Well, that's actually counterproductive. And the reason that that's counterproductive is because, you can't see a terabyte, much less a petabyte, and I'll explain why. One, there's a depth complexity problem and there's a spatial complexity problem. Okay, so you may have a hard time seeing this, this image. There's a person looking into this complex scene from this side. Yeah, you guys aren't going to be able to see that. Anyway, the idea is that there's a bunch of stuff in this scene, and as they look through it, the number of objects that they encounter along a particular line of sight is, in fact, the number that's used to compute depth complexity. So with a terabyte, if we're going to compute an isosurface of a terabyte's worth of data, 1K cubed grid of data, we know from our studies that the depth complexity of that isocontour is going to be on the order of 2 to 20, right? So in other words, it's going to fold over itself, 20 times in depth on average, or between 2 and 20 times on average. And because of occlusion, you can't see it, right? Now, if we go up to, if we increase by a factor of 4 in each dimension, the depth complexity just goes through the ceiling. And what I mean when I say we can't store it is for certain types of graphics visualization algorithms, we're going to rely on the frame buffer to accumulate data as we render it. And so these things typically have 8 bits per color of 8 bits per resolution per color. And pretty quickly we're going to run out of bits of resolution, and so this carefully computed image is going to disappear. So we've wasted our graphics hardware and time trying to make a picture of something we can't see. With spatial complexity, the problem is that these mesh cells map to something that's smaller than a pixel, so you can't see a mesh cell. So the community is answered by creating these high-resolution displays. Well, you have to stand at a certain distance from those things to gain their full benefit. I mean, the TV manufacturers worry about this a lot. The new plasma displays, they want you to stand 6 feet away or something. It's just not a practical problem. So our visualization program here takes aim pretty much at all aspects of the problem space that I've talked about here. There's one effort that's the DOE SIDAC Visualization and Analytics Center for Enabling Technology. We also do work for the NERSC Center doing visualization and analytics, and we have a base research program in high performance visualization research. All 3 of these programs live in synergy and harmony with one another because you can't really pull one out and have it be successful in a vacuum. So just a couple of more slides about the road ahead. One of the challenges that we face is effectively leveraging the new platforms that are coming out. So there's exotic systems like the Cell BE broadband engine platform that's on the PlayStation 3, the GPUs obviously, and you might think, well, I just read a paper, or I heard about, somebody did something really amazing on a GPU. Yeah, those kind of things are happening all the time. But, at the end of the day, Sylvia has to be able to sit down and use a piece of software without me holding her hand to do her science. And so we're a long way from being there. Franklin at NERSC is a 19,000-way parallel machine. Can we effectively use that for doing visualization? I'm not sure. That's an open research question. With hierarchical parallelism, what I mean is multi-core. So, projections have single CPUs containing 16, 32, 64 cores in the not-too-distant future. Is visualization software ready for that? No, I don't think so. I think we got a lot of work to do. Okay, so that's the meat grinder, right? Now, what about creating techniques that are actually more effective at presenting information? Okay, so here's an example that shows combining visualization with data analysis. This was done by Oliver Rubel of our group, who's Oliver's back in the back. This is 3D gene expression data, and there's 3 different views. There's a sort of a physical unrolled view that's colored by the results of a clustering algorithm. I hope I got that right. Scatter plot of 3 genes, also colored by the results of clustering. Interesting parallel coordinates plot that show a different view of the data. So there's 3 different views of the same data set here, and each one conveys information in a unique sort of way. So another huge problem is one of usability engineering. And so this problem is actually bigger than it might seem as you first look at it. You might think, well, this user interface is, well, it's not just user interface. It's also the guts of the machinery that's underneath it. So, there are no data format standards in the scientific world. There's conventions that are adopted by ad hoc groups. And so what this means is that people who write visualization software have to deal with a million different data formats. It's crazy. We spend just way too much time dealing with this problem. What about programming interfaces so that we can bolt together software components that come out of the research community? Well, this is a hard problem. It's hard enough on a serial machine, and it gets worse as we move into the world of parallelism. And then, of course, the user interface problem we can't get away from, and it's not just stuff on the screen, but overall user interface. So the story that I told about my uncle's buddy in the oil business who was driving the simulation, that was effective because I really didn't have to give him much instruction, and he was able to effectively control a complex piece of machinery with just a couple of knobs and buttons. This example is from Google Earth, and so here we have a zoomed out view of the Earth, and if we zoom in, then we can obtain some demographic information about a particular region. I saw an interesting example of using Google Earth to explore what had been happening over in Darfur. So you could track the effects upon individual villagers and villages. So it was very amazing. And that's it. Thank you very much for your time. We'll see you next week, or next time.
We got time for a couple of questions, but please wait until either I or Lynn Hunter's going to help me out here.
Hi, how many examples are there like your petroleum, your drilling example, where the machinery and the interface work really well together?
Yeah, so that's a pretty good example. There's lots of them. I'm unable to improvise off the top of my head and rattle off more, but with a little bit of effort, we could generate a long list of them. Yeah. Don't give the microphone to Jed.
So it seems like the mathematics that you went through early on is pretty simple and was probably understood before the computers started getting good enough to do some of this stuff. And so a lot of the work seems like what you called the meat grinder. Where are the, I don't know, the Nobel Prizes or that sort of thing? Where does the excitement come through in computer graphics? Are there breakthroughs that are happening?
Well, the computational geometry, the computational topology involves complex Morse-Smale theory, and that's actually very dense mathematics, which I didn't show you because I wanted to be nice to you.
I just wanted to give an example of the previous question. I think
Yes.
Medical imaging and like a lot of the virtual surgery is a great example where the visualization is just as important as like these haptic interfaces and things for people to, you know, really interact with the environment just like they would practice for surgery and things like that. So like there's a really big intersection there between the math and the modeling of the surgery and the visualization, I think.
Right. So there's like some examples come to mind now that you mention it. There was Henry Fuchs at UNC Chapel Hill that was working on an augmented reality system to do needle biopsy for breast cancer type applications. Another was it was right on the tip of my tongue. Ari Kaufman at Stony Brook, virtual colonoscopy. Right, so that would be something that would be very nice for a lot of people to be able to take advantage of. Yep.
Here's one more.
Will the summer talks be available to look at online?
Paul can answer.
My understanding is that we will post them online pretty soon. And as soon as we get the edited presentation back from the people who are doing the video now, and there'll also be a broadcast on UBC television out of Davis. That'll probably be a few months from now, but they should be up pretty soon on the website. Just the slides. I'm a little vague about that. We could do that.
I can give you a copy.
Yeah, okay.
Well, they'll be on our YouTube site, won't they?
Yes, they'll be on the video. The video will be on the Web Center YouTube site. If you're familiar with our new website, there is a news center on there, and you just go to the news center and you can. YouTube. Well, it's YouTube. It's a Berkeley Lab YouTube account. Yeah. Yeah.
Wes, I realize that you're doing visualization and the major sensory organ that you're using are the eyes. But with very complex analytics coming up, is there any tendency in the field to add another layer, like sound mixed in with a visual?
Yeah. So that's an interesting question. I may invite some of the guys in my group to jump in here. So sound is good for indicating binary events, right? So is my landing gear down? Did something blow up? And it's not as good as representing a discrete or a field of data. Your ears are not as well adept at integrating sound as your eyes are at integrating visual light. Now, of course, you can have complex tonal combinations, chords, majors, minors, that sort of thing, for indicating multiples of binary events. But using it to go after terabytes worth of data, I don't think there's much of that going on in our field. Do you guys know of anything? Yeah.
There have been studies showing, this is a problem that people have been looking at for some time, and many studies have been done over and over again as to what are the uses of other senses, sound, touch, and it can be used in there are some dimensions where you can use other sensory input, but in terms of large amounts of intellectual information, nothing beats the visual channel.
Yeah. There was an article in Wired magazine a couple of years ago about an interesting output device that consisted of, did you ever do creepy crawlers when you were a kid? You had the plastic goo and thing, right? So it was like a creepy crawler oven that had 8 different smell pots in it, right? And you could burn different, combinations of smell pots. It was smell-o-vision. And it was an interesting novelty, but I don't think it really took off. Yeah.
Well, with that note, I think we have to call this one to a halt. Thanks a lot, Wes Bethel.